Microwave tubes, Magnetrons, Part 2, series on microwave engineering, lecture number 4.32. Magnetrons are high power, high efficiency microwave oscillators, microwave tubes. Cavity magnetrons, also known as cylindrical magnetrons. These are the type of magnetrons that are used at present. These devices are basically diodes having a cylindrical rod, thick rod as cathode, surrounded by a cylindrical thick block of copper as anode. The structure of the anode consists of several identical cavity resonators. These resonators are interconnected with each other through the interaction region that exists between cathode and anode. When cathode is heated, electrons get emitted. These electrons then form into bunches. Not all electrons participate in the bunching process, only some of the emitted electrons. They come together and form into bunches. These bunches then deliver energy to the rotating RF field that exists in the interaction space. The energetic rotating RF field is then taken out for further use from one of the cavity resonators with the help of current loop. In the present session, the focus is on a description of functioning of cavity magnetrons, on strapping mechanism, and also on variation of frequency of the device with anode voltage or current, and also with load admittance. Now let us move to the core session for further discussion on the functioning, strapping, frequency pushing and pulling of cavity magnetrons. Let us start with the functioning. When the values of the static fields are adjusted properly, the electrons follow cycloid paths in the interaction space. In the interaction region, apart from the rotating RF field, there exists two static fields. One is radial electric field like this. Another is axial magnetic field. This is electric field, this is magnetic field. One can easily notice that these two fields are perpendicular to each other. When an electron is emitted by the cathode into the interaction region, the electron finds itself in a region where crossed fields are existing. Under the influence of these two crossed fields, the electron moves in a path. That path is called cycloid path. So electrons move in cycloid paths in the interaction space under the influence of crossed static fields. Acceleration of the electrons by the direct electric field and retardation by the alternating field takes place simultaneously in the same interaction space. Notice the purpose of electric field is to accelerate the electrons or to give energy to the electrons. Initially, when they are emitted, energies of the electrons, they are very small, but electric field gives acceleration to the electrons, raising their energy levels. These highly energetic electrons then transfer their energy to the rotating electric field, RF field that exists in the interaction region. Of course, before that, some of the emitted electrons come together forming into bunches. The bunches then deliver energy to the RF field. The point here is acceleration of electrons, that is giving energy to the electrons by static electric field, and retardation of the electrons by alternating field, that is transferring energy to the rotating RF field by the electrons. These two take place simultaneously in the interaction space. The crossed fields cause the electrons to be completely bunched almost as soon as they are emitted. The bunches then move along the traveling wave field with almost at the same speed and deliver power to the field. The RF power is then extracted by placing a coupling loop in one of the cavities or by coupling one cavity directly to the waveguide. Ultimately, what is happening here is energy transfer takes place from DC electric field to RF field via electron bunches. Before moving further, one point is required to be mentioned here. Purpose of static electric field is to accelerate the electrons, to energize the electrons. Purpose of static magnetic field is to focus the electrons. The purpose of rotating RF field is to accept the energy by retarding the bunch movement. During retardation, energy transfer takes place from electron to RF field. Now, some more points regarding operation. Usually, the device is operated in pi mode. Cavity magnetrons can be operated in different modes, but the one that is preferred is pi mode. Why it is called pi mode? Reason is two poles, side by side poles in the anode structure of the device. They exhibit a phase difference of pi when the device is functioning in this mode. For this reason, it is called pi mode. Most of the times, device is operated in pi mode. Now, a few points regarding functioning of the device in pi mode. Self-consistent oscillations can exist in magnetrons only if the phase difference phi between the adjoining anode poles is n pi by 4. When n is selected as 4, phi becomes pi. Then that particular mode of functioning is called pi mode of operation. The connected re-entrant cavities are conducive for the generation of a rotating RF field in the interaction region whose angular frequency is beta naught multiplied by d phi by dt. This product beta naught d phi by dt, it gives a certain frequency. This particular frequency is the frequency of rotating RF field. Here B naught or naught is phase constant. Phi is phase difference between the side by side anode poles or adjoining anode poles. Beta naught is 2 pi n by nl. Here n is mode of oscillation, n is number of cavities, L is mean separation between the cavities. One can notice here phi depends upon n, omega depends upon phi, beta naught it depends upon number of cavities and also mean separation between the cavities. Omega also depends upon beta naught. So the point here to be kept in mind is the frequency of the device. It can be controlled by selecting proper value for L, proper value for N, proper value for small n2. Now, for energy transfer, cyclotron angular frequency omega c, E by m multiplied by B. This product is called cyclotron angular frequency omega c. It must be equal to angular frequency of the field. Angular frequency is beta naught d phi by dt. So through B also, that is axial magnetic field also, one can control the frequency of operation of the device. The conclusion is this: noise is everywhere. Noise is in the interaction region too. Noise can be considered as combination of several frequency components. The amplitudes of these components are usually negligibly small, but one out of these several components can be picked up for strengthening. This selection, it is through the selection of small n, capital L, capital B. Only that particular frequency component, it becomes capable of accepting energy from the electron bunches. It is then taken out of the device with the help of a current loop. For best results, n equal to 4 is used and the resulting mode is known as pi mode. This mode is preferred in practice since it can be readily separable from other modes. In this mode, the RF field has a phase difference of pi between two successive poles, side-by-side poles, and also between adjacent cavities. The straps are able to provide stability since they connect all the poles of anode which have same potential, thus forcing the tube to remain in this preferred mode. Pi mode is associated with certain positive aspects like the device can be made to work in this particular mode easily by providing strapping to the device. Another aspect that favors pi mode operation is this is easily separable from other modes. For these reasons, pi mode is preferred. Now here is shown magnetron placed in cylindrical coordinate system. This is all interaction region. This is cathode. A is the radius of cathode rod. B is the radius of anode or inner radius of the anode. The voltage V0 is connected across cathode and anode. Notice negative battery, negative terminal is connected to cathode, positive to anode. A magnetic field, DC magnetic field is, it is applied to the device. The magnet is not shown here. Therefore, in the interaction region, there exists a radial electric field. Radially inwards, the electric field is like this towards the cathode, and an axial magnetic field. And because of noise, one rotating RF field also exists in the interaction region. In B is shown the paths of electrons in the interaction region. After emission by the cathode surface, electrons find themselves in the interaction region where there exist crossed fields. Under the influence of crossed fields, they move in specific paths. Paths of 4 electrons are shown in this diagram. This is path of one electron, path of another electron. These 2 electrons, after getting emitted, they spend some time in the interaction region and they return back to cathode. These 2. Whereas other electrons, they reached anode, grazed the surface of the anode and returned back to the cathode. Another electron also returned back. Path of electrons, path of electrons. 2 electrons, they touched the inner surface of the anode and returned. This happens when the static fields, they assume certain specific values. Those values are called cutoff fields, Hull cutoff fields. When field strengths are less than cutoff values, then electrons follow the paths similar to the paths of 2 electrons that are shown here. Path of electrons below cutoff. So at cutoff, grazing with the anode surface takes place. Below cutoff, electrons, they are unable to reach anode surface. Without reaching, they return back to the cathode. Cutoff fields, they have certain special significance, importance in the functioning of the device. A few points regarding Hull cutoff fields. Hull cutoff fields are values of anode voltage and axial magnetic field necessary to return the electrons to the cathode after grazing the anode in the absence of RF field. Hull cutoff voltage for a given axial magnetic field Bz is given by symbol is VOC. E by 8m. E stands for charge on the electron, m stands for mass of the electron, Bz square b square into 1 minus a square by b square whole square. Bz is axial magnetic field, B is anode inner surface radius, A is cathode radius. If V naught is less than V naught C for a given Bz, the electrons will not reach the anode. Here A and B are radii of the interaction region. Now Hull cutoff magnetic field for a given potential difference B naught is V naught C symbol, it is equal to 8 V naught m by E square root B into 1 minus a square by b square. The meaning of various symbols that are appearing in the expression, they are already given, known to us. It doesn't require further repetition. If B naught is less than B naught C for a given B naught, the electron will not be able to reach the anode. A few points regarding strapping. Presence of n cavities in the magnetron gives rise to n by 2 possible modes and an equal number of different RF field configurations. Each one of these field configurations except one pi mode can oscillate at two different frequencies. As a consequence, the magnetron with n cavities can oscillate at n minus 1 different frequencies. Unless proper precautions are taken, there is a possibility for the tube to oscillate at one of these frequencies in an unpredictable manner. Also, there exists a possibility for the oscillator to jump from one to another frequency in a random manner, causing instability. The basic point here is the device can function in one of several different modes. These modes are associated with two frequencies, except of course pi mode. Unless proper precautionary steps are taken, there is a possibility for the device to function in a mode which it is not expected to be in, and also as it is in a mode different from the mode in which it is supposed to be, its frequency also is going to be different. This is one issue. Another issue is the device may start functioning in the mode in which it is supposed to be in the beginning, but later there is a possibility for it to jump into another mode, to function at another frequency. This mode jumping happens, possibility is there, to occur in an unpredictable manner, random manner. This is another issue. So all these issues, they are to be attended. Precautionary steps are to be taken to prevent happening of these difficulties in the functioning of the device. Strapping is a technique, a simple one, which is a solution to the unpredictable functioning of the device in an unwanted mode, as well as for mode jumping. Some more points regarding strapping. To prevent operation at unknown frequency and to avoid mode jumping, strapping is employed in magnetrons with identical cavities in the anode block. For pi mode of operation, it consists of two rings of heavy gauze wire called straps connecting alternate anode poles. They improve the stability of the device by preventing mode jumping and also increase the efficiency of the tube. The effectiveness of straps in separating frequencies of various modes is expressed in terms of weight of strapping, or simply weight, strapping weight. If the straps produce large increase in mode separation, they are called heavy straps. And if they produce a relatively small increase in mode separation, they are called light straps. Increase in strap capacitance and or decrease in inductance causes the increase in mode separation. Thus, strapping weight depends upon capacitance and inductance, which in turn depend upon the length, separation, and cross section of the straps. It also depends upon the number of straps and the points on the resonator poles to which the straps are connected. Now, after strapping, a few points on rising sun resonators. What are these rising sun resonators? At very high frequencies, the dimensions of the resonators become very small and the use of large number of resonators become inevitable. So dimensions come down and the number increases. Consequently, the design and construction of strapped resonator systems become cumbersome. It is difficult. In magnetrons working at about 10 gigahertz, the resonators are unstrapped because strapping becomes a difficult process. For the reason that now dimensions of the resonators are small, numbers are large. In magnetrons working at 10 gigahertz, about 10 gigahertz, the required mode separation is obtained by the use of rising sun resonators. In these systems, the natural frequencies of adjacent resonators differ, but alternate resonators are like this. Anode structure itself is used to prevent mode jumping. Here is shown the structure of rising sun resonator. In C is shown rising sun resonator structure. Inside the anode block, one can see several resonators. Notice alternate resonators, they are of same size and shape. All alternate resonators. Some resonators are small, some are big, but all alternators are of same size and shape. The small resonators, these are all same size and shape. Slots. Slots are acting as resonators. Cavity is in the form of a slot here. Of course, cathode exists somewhere here. In this diagram, some other types of resonators are also shown. In A, vein type is shown. These are veins. These protruding fingers, these are called veins. In B, slots are there in the anode structure. A and B, they are suitable for strapping, whereas C, it is used at high frequencies. AB are at ordinary frequencies. Now, a few points regarding frequency pulling and frequency pushing. What is this frequency pulling, frequency pushing? Frequency of the device, magnetron, depends upon anode voltage, anode current, and also load admittance. If anode voltage, anode current, it is varied, frequency varies. If load admittance is varied, then also frequency varies. The dependence of frequency on anode voltage, anode current, and load admittance. This particular aspect is measured by frequency pushing and frequency pulling. Now, a formal definition, a formal explanation, description of these two terms. First, we consider frequency pulling. What is frequency pulling? The resonant frequency of the magnetron is dependent upon load admittance. Variation of resonant frequency with load is known as frequency pulling. How to remember pulling, pushing without confusion? In pulling, L is there. In load, L is there. So frequency pulling can be connected with load. Frequency pulling refers to change in frequency with load admittance. A measure of impact of load on magnetron frequency is pulling figure. It is defined as difference between maximum and minimum frequencies when phase angle of load changes through 360 degrees for a fixed VSW value of 1.5. It can be obtained from Rick diagram by mere inspection. Now, frequency pushing. The frequency of magnetron is also dependent upon anode voltage and current. Frequency pushing is a parameter representing variation of frequency of the device due to change in anode voltage. By definition, it is change in oscillator frequency produced by a change in anode current for a fixed load. This parameter is often called pushing figure, and a plot of frequency versus current is called pushing characteristic. The slope of this curve represents the pushing figure. For better frequency stability, pushing figure must be low. Pulling figure also, it must be low. These are some of the things which I want to share with you in this session. second session on magnetrons. To recap, here we focused on functioning of the device, strapping of the device, and also frequency pulling and frequency pushing. Enough for now. See you soon again in another session. Hope you have a beautiful, enriching learning experience. Bye bye.